every those things are happening.
All right, welcome back to the second talk. We're continuing with Nadir.
Thank you. So I'm going to talk about reference points. Maybe first for the algebraic groups, there's also a useful reference, which is less valuable. It's a book of classification of some you do something like this. And so for the topics I'm going to discuss, there are lots of Indra Prasad and run which will give slightly more proof than what I gave. And for more details, we have notes of well-known notes of Hefferman. And for very much details, we have a book by David Lamar. So these are for GLN and these are for reductive groups in general. Yeah. So I'll start first with Jacquet modules, which are already introduced. So there's the local analog of the constant term, whereas those twisted coinvariant that I had introduced, the VH side, there's somehow the local analog of Fourier coefficient of the Eisenstein series. And so so you take the representation of Gn, and so a Jacquet module will be a space like this, V, U, and bar. So I hope you remember the notation. It was just the quotient of this, and so it's a representation of the corresponding standard Levi group. And I will denote by J, sorry, U and bar of G, the twisted representation by this character. Because I normalize parabolic induction, I have to normalize Jacquet module.
What does Q and bar stand for? Does the bar stand for opposite?
Yeah, so and bar is a sequence like of positive integers like this, and one and r with a sum of ni equal to n, and un bar is the unipotent radical of the corresponding standard parabolic sequence. And so, yeah, as I said, in general, if you put the character here, this is a representation of the normalizer of the character. So here the character is trivial, so somehow it's just a representation of a normalizer of this, so it's certainly a representation of the Levy. And so from Frobenius reciprocity, you easily deduce that this Jacquet module is adjoint to the parabolic induction counter. So a statement like this will naturally be isomorphic of for phi in part Tn and sigma in R Mn bar. Okay, and so more generally, you can define Jacquet modules for a representation of Mn bar. This will be cumbersome because I'm doing very GNN stuff, so it would be easier to introduce the notation for a more general setting. But so if I take for each Ni another Ni bar, and if I take I don't know, sigma representation of R and bar, which is just a product of GLN, right? Then I can define, let me imagine what this would be, R, M in bar, U in one bar, times U and R bar of sigma, defined similarly. So maybe I can write this as U and one bar and a bar. And so I didn't mention that parabolic induction has a transitivity property, and so Jacquet modules have a similar property. So exercise. You can check that if you start with something which is in RTN, and you apply a first Jacquet module. So here you end up in R Mn bar, and then you can apply a second one like this. J Mn bar, sorry, that's the U. U and one bar and R bar. Okay. Then it's the same as if you start from Gn and you go to U. So I hope you understand. This is a partition of N consisting of you add up the subpartitions there. Okay, so you have this transitivity property. And you can write the same property for parabolic induction. Okay, so just for the sake of culture, I will take the Fermat theorem on papier. I think we really did it for GLN, which says that if you start with an admissible representation for in HN, then the
representations are admissible.
no, they're smooth.
Oh.
And R is for smooth, A is for admissible, and so the Jacquet module will be admissibility. I will give you proof. And in fact, if you start with an irreducible representation, then the Jacquet module will not be irreducible, but it will be of finite length. So I write F and finite length representation of GL. And if you remember, those Jacquet functions, they are exact because those groups are exhausted by compact subgroups. So if you start with finite length here, you end up with finite length of them. Okay, and a remark is that a remark is that you remember if phi is generic in the asymptotic expansion of the Whittaker functions of the inside the Whittaker model of phi, there was a set of characters E of phi. It was a set of some characters of F star. And so I just want to say that they're closely related. To the central characters of the irreducible subquotients of G, U, N bar, E, N, phi. When N bar varies among those partition of the form N1 and
This exceptional set for which the intertwining was not working well.
no, it's different set. This was the notation for a set of characters of F star, which naturally occurred in the asymptotic expansion of Whittaker functions. I gave at some point an asymptotic expansion of Whittaker functions 2 lectures ago, and I introduced this notation.
I will feel to remember.
It was to justify the convergence of Rankin-Selberg integrals. Okay, so now we'll talk about custodial representation and custodial support. So the definition of a custodial representation. General definition, you take pi as smooth representation. You say that pi is custodial if the Jacquet modules of pi are non-zero. All Jacquet modules associated to proper parabolic subgroups are zero. So this is the definition of the custodial representation. And you have a similar definition for that we maintain for sigma in R and bar. And so, in general, what happens if you type start with a 10 reducible representation, and then if it's not custodial, then there is at least one Jacquet module which is non-zero. But by transitivity of Jacquet module, either the Jacquet module that you get is custodial itself, or you can apply transitivity and find another non-zero Jacquet module. And so you will end up with by transitivity of Jacquet functors. You will finally define there is this N bar such that the Jacquet module associated with this partition, so pi, will be custodial. in fact of finite length because we started with something irreducible. Just by a very simple induction. And so my Jacquet module is a custodian of finite length, so it says I take one irreducible quotient. So take irreducible quotient of the Jacquet module. Then rho is certainly by definition an irreducible representation of Mn bar, but it is again custodial by exactness of the Jacquet functors. And so you end up with a non-zero intertwining operator from the Jacquet module pool. This case is non-zero. But this is the same as this case. I Mn bar GL rho, and because phi is irreducible, if you have a non-zero intertwining operator, it is injective automatically. So phi appears as a submodule of a representation induced from a custodial representation of a Jacquet. This representation is irreducible custodial, right? So this is the first step towards a very easy step toward the classification of irreducible representation. But if you really want to talk about classification, you would like some kind of uniqueness property for rho there. So this is the theorem due to Bernstein and Levinsky, and also probably independency Kasserman. So I will state it under this form. So take an irreducible custodial representation of some Levy, Mn bar 1, Mn bar 3, and rho prime, an irreducible custodial representation of some other Levy. I'll put a prime there. Maybe I give a name to the partitions. So this is N1 and R as before. And this is N prime 1, N prime S. And so then I can consider the induced representation to Pierre of both these rho and rho prime. So yeah, I'm going to mention it right now. So Jacquet function take irreducible to finite length, and the same goes for parabolic induction. So they're finite length. Sorry? Rho prime, yeah, sorry. So in fact, they both finite length. They have a irreducible subportion in common if and only if there exists G in Gn. In fact, you can take it in the Y group WN, which is Sn there, such that Mn bar prime is conjugate to Mn, and rho prime is isomorphic to rho W minus 1 W.
The G is a W.
So the yeah. And so very explicitly, if I want to use the partitions, so rho is an irreducible representation of a product of Gn1 times Gn2 times Gnr. It is well known that it decomposes as a tensor product. I can write rho like this. And I can also write rho prime, rho 1 prime. This was an S, right? So rho S prime there. And so this condition just means that first of all, R is going to be equal to S. The last condition will be that R is equal to S. And there exists sigma in the symmetric group on R letters, such that rho prime I is equal to rho sigma I. Okay. And so you see, here I started with a irreducible representation, and it embeds as a sub of rho. Okay. And so this theorem says that rho is somehow unique. In fact, it says exactly this. So call yeah, or set. Consider the following multiset. Multiset means it's a set, but you can have repetitions. Okay. And P, an irreducible representation, as a such that phi embeds in I and bar Gn rho. Then this multiset is unique. If I have another such embedding in some rho prime, then the corresponding implicits will be the same. And it's what I call it the cuspidal support. Right. So any pi embeds in a representation induced by sometimes people call this a representation, write this representation like this, just with product notation. And so it means that if pi embeds in a product like that of cuspidal representation, those cuspidal representations are very unique of the order.
This means that even if the curves of the portion, it will be the same support.
Say it again.
defines a sub-portion of the rho.
Yes, absolutely.
The rho is the same as Caspidal support.
Yes, and that's why. So some people say that oversee cuspidal and supercuspidal representations are the same. Over some other fields, being a subportion of such an induced representation might be different than being a different cuspidal and supercuspidal.
Is there an easy criterion with respect to those rho for this induction to be reducible? Or irreducible?
No, I mean, I will not really talk about this, but this is very well understood thanks to the work of Bernstein and Zelevinsky
For GLN.
for GLN, yeah. And for classical groups, it is more and more well understood in general. Yeah, I gave the general criteria for general principal series.
Yeah. No, I was asking in general, like for some reductive group G's.
But yeah, for an induced representation from cuspidal representation, the criterion is just the same because you're inducing from cuspidal representation. Okay, so this was the uniqueness of cuspidal support. And so to make a relation with what I said yesterday about representation with the Iwamoto fixed vector. So I said that the two representation P and phi prime, which are irreducible, are inertially equivalent if their cuspidal support are equal up to unramified twist. So this means that if I take the cuspidal support there and the cuspidal support there, up to reordering, I will have a relation like this. And so yeah. So a Bernstein block in the category of smooth representation is an indecomposable block. And so one thing is that by work of Bernstein.
The Bernstein block is equivalent class with respect to this relation.
Sorry?
A Bernstein block is an equivalent class with respect to this relation.
I'm just going to state. So pi and pi prime, at least I just suppose them irreducible. Lie in the same Bernstein block. If and only if they are inertially equivalent. And so for the Iwahori or RTIN, the corresponding supercuspidal support up to this equivalence class is just trivial character of T1, trivial character of T1, trivial character of T2. So now it's the classification. There are two, this is a specific feature of GLN. There are two classifications, one which is called the Zelevinsky classification and the other one which is called the Langlands classification. So I will talk about the second one. So So if you start with the custodial representation, irreducible. Of some GM, say. And you take K, an integer at least equal to 2, and you consider I, M, and bar of new 1 minus K over 2, and you go up by 1 every time. You want this to be symmetric somehow. Yeah, sorry, new is absolute value of determinant. Then this representation has irreducible crossover. It has a unique irreducible quotient, which I denote by STK of rho. This is called the generalized Steinberg representation. So at this point, I'll make a remark, because there are many definitions of custodial representation. And some are, the one I gave is algebraic, but there are analytic definitions. So remark, these are results of Bernstein, Zelinsky, and Kasselman. An irreducible representation of GN is considered if and only if it has one matrix coefficient a compactly supported mod center.
Should replace one by non-zero. A non-zero matrix coefficient.
Yeah, okay. Again, depends on if you consider a zero as a matrix coefficient or not. I will give my definition of matrix coefficient.
Say one, who says there's only one?
No, and equivalently, if all matrix coefficients are compactly.
So your definition of matrix coefficient doesn't have to be zero.
Sorry?
Your definition of matrix coefficient doesn't have to
Yes. Well, I will give the definition after the statement. Or if you like non-zero. Okay, and one says that so it is going to be slightly different than what Raghuram said in his book, is a discrete series representation, or let's say the discrete. If it has one non-zero matrix coefficient C such that some unramified twist of it, which satisfies that this integral is finite. Or equivalently all its satisfy this. And so what's a matrix coefficient? It's a function from Gn to C of the form C of G So if I want it to be non-zero, I must take VH non-zero and D non-zero. Or VH in ROCH. So maybe this one. Put pi here. VH in pi H. Pi. And to say that it's non-zero means just that both these vectors are non-zero. And so the general Strasbourg representations are the discrete series of GNF. Representations of the form STK rho as a discrete series of GNF. And that rho is unique. STK rho is come from any place of particular supporting, right? If STK rho is isomorphic with STK prime rho prime, it implies that K is equal to K prime and rho is equal to rho prime. So now we have the description of discrete series of GNF in terms of cluster representation. There are irreducible quotients of induced representations of this form there. So now we define what the standard module is. But first of all, I will introduce a notation. So notation. If delta is a irreducible discrete series, I'll put this here, DISC. There exists a unique real number, just from the definition of discrete series, such that determinant minus E of delta times rho times delta is square integral satisfied is uniquely same. But in fact, it's square integral. It means it has a coefficient which satisfies this direction, right? And so now I can define standard modules. The standard module of Gn is a representation in RGN, in fact, in finite length representation of Gn of the form IM bar Gn delta 1 times delta P, where the delta I is a discrete series. Such that the sequence of real numbers that I just defined there for each discrete series, there's a unique E delta like this, form a decreasing sequence. So I can now state the nominal classification of irreducible representations of GLN. So theorem, which is due to Bernstein and Televinsky in the context of GLNF, but in full generality, it is due to, I don't know if I should say Silberger or Silberger, probably. The theorem or general reductive groups. And I will state it more in the way Silverhead does. Which is called the Langlands quotient theorem. Is that if S is a standard module of Gn, then it has a unique irreducible quotient. LQ of phi, LQ of S, which are also sometimes write phi of S. So this is the first part, and the second part is that the map S goes to the non-Lagrange quotient of S is a bijection. From the set of isomorphism class of standard module of Gn, these are isomorphism classes of standard modules. RGN. So here in this talk, RGN is really isomorphism classes.
So something is a little bit fishy because if two of the EIs are equal,
Yes.
it's like E1 equals E2, you're
Yes.
allowed to permute, right?
Yes.
But if delta 1 and delta 2 don't have anything to do with each other, you'll get the same Lagrange quotient. So
Yes.
it doesn't seem like a bijection.
Yes, but the standard modules, though they don't look the same, they will be isomorphic.
I'm saying you can just take T equals 2,
Yeah.
like delta 1 and delta 2,
Yes.
okay? And then what you're saying?
It's a body equivalence. This is exactly what you know.
Oh.
First of all, there's this condition which is restricted, and
Okay, so you
well-
know what I'm saying, it would be a irreducible thing already, that's what you're saying, okay, it's modular equivalence.
okay.
When do you say the two standard modules are equivalent?
Isomorphic, yes, as GN representations. So yeah, now I want to make the relation with the Lagrange correspondence. So I will introduce some convenient notation. So rep WDF will be the set of Lagrange parameters. And as I said, it was semi-simple representations of the Vierteling group of finite dimension introduced in at the end of the first lecture. And I will add an n to say that there are dimension n of dimension n. And so for phi in irreducible representation, I will denote by phi of phi, it's n parameter. And for phi, an n parameter of dimension n, I will denote by LHC of phi. LHCn of phi. It was the map LHCn that I defined before. And more generally, I define LHC of phi for phi a net parameter B LHCn of phi if phi has dimension n. So I have a map LLC from rep GF to the disjoint union of RGN when n varies. Okay, and so I'm going to state some results which are well known. So rho is considered if and only if it's a L parameter. Cusp is an irreducible representation of WF. So it means it's an irreducible representation of the veil de Limbourg trivial on SL2 of C. Irreducible and on SL2 C.
I don't know if everyone remembers that WD is WF times SO2C.
All right, this. So a second discrete series correspond to irreducible representation of the veil de Limbourg. And so, in fact, if delta is of the form STK rho, this will correspond to phi of rho times the product SPK. This was the k-dimensional irreducible representation of GA to C. And finally, if phi is an irreducible representation, so I can always write it as the Langlands quotient of a standard module. Sorry, what's this? What is I MN bar N. Yes. So any reducible representation can be written in such a way uniquely. Then the corresponding Langlands parameter will be phi of phi is the direct sum right from 1 to R of phi of rho I and P and I. Okay, and so I'll give you a second exercise. If you admit everything I said before, you can do it. And, So first, you can remark that the irreducible representation of WF, which have a vector fixed by the inertia. These are just the characters of WF divided by IF. And so by R10, which is LLC1, these are the unramified characters of one star. And so the second thing is that by an irreducible representation has a fixed vector under the Iwahori.
The first one, you're in dimension 1 or?
No, in fact, if you're in any dimension that you have a vector fixed by the Iwahori, you're automatically a character because the Iwahori is a normal subgroup.
You write something, like right, this non-zero equivalent, I don't know, like this sentence, this equals to that, what do you mean?
No, this check is an exercise that all irreducible representations of WF.
Category is equal to the.
No, this is an equality. I'm saying this is a part of the exercise.
Equality of what, like on the
So
right.
let me say what I mean.
You have like a category. I mean, like there's abuse of notation at the very least.
Okay, so what I mean that check that an irreducible representation of WF with a vector fixed under IF is automatically a character. That's what I mean. It automatically has dimension 1. And second, check that an irreducible representation has a vector fixed under the Iwahori subgroup. If and only if phi of pi is trivial on IM.
Just for a student, it's a very difficult notation you're using that, like you take some category and you put like invariant by some group, which means like that.
Okay, so it's
the category which has invariant by the group. It's kind of, I don't know, like it's on another categorical level notation series. It's
irreps of F. IF fixed vector. And this is the same irreducible representation of Gn with an IN fixed vector. And so I will end up by a characterization of the LLC, which is due to Henya. There are more recent ones which I don't understand. This one I do.
no, you're doing like very high-end exercise. I mean, a much easier maybe thing to maybe write the answer as an exercise. It's like, what is the trivial representation for GL2 in this classification? Like, what's the parameter of the trivial representation?
So the trivial representation of GLN. GLN is the long loss quotient of ITN EN n minus 1 over 2, 1 minus n over 2. And so by what I said, the Langlands parameter of the trivial representation is the direct sum of these characters. Here I use a LLC1, I use a in response. So this is due to Genya. So you can define on the Galois side, one can define. So I will give the definition, which Mladen already gave of Artinel factors of objects in WTF. So first of all, you want them to be additive. So you want LS of phi1 plus phi2 to be the product of the factors. And so if you want this, I just need to define them for irreducible representation. And LS of phi an irreducible representation of WF 4 times XP n will be LS, so that the translation is by n minus over 2 for phi, where LS of phi was defined by Mladen. So it's 1 over the determinant of so ESA phi is n-dimensional. What am I right here? I look at the I'm not sure what to put here. It's minus q to the minus s phi of the Frobenius restricted to v phi if. And so here I put the identity of this space. It's correct, right? Okay, so this is the definition of the Artinel factor of representation of the region group. And there's also a definition of epsilon factors due to Langlands and Deline. So this I will safely skip. But you can also define. Yeah, I'll take 2 more minutes. Deline and Langlands in different manners. Fine. For phi and n parameter. And psi non-trivial additive character of F. Okay, and so now I can say the linear classification. So theorem. Okay, now. Take for each n a map I n from rep n WDF to a set of irreducible representations, one isomorphisms on both sides of Gn such that phi1 is equal to LHC1. So this is the first thing. And the second thing is for all n and n prime maybe I can put n greater than n prime greater than 1. LS of phi times phi prime is equal to NS of phi n phi n prime phi prime for any phi n rep n WTF and any phi prime in ref n prime WTF. And the same condition on the epsilon factor. Same condition on epsilon. Then phi n is LHCn for all n. So the Langlands correspondence is characterized by equality of Rankin-Sedberg L factors and RT in the lean Langlands local constants. But you have to require it to be equal to the RT map on GM.
Well, let's thank Nadia. I can add a thing for students who maybe aren't that familiar with this. When Odell, Harris, and Taylor, maybe 20 years ago, proved local Langlands correspondence for GLN, they had to use global methods. But you cannot take a random local representation and put it into an automorphic form. So they only proved it for supercuspidal representations. And it was this theorem of Enyart's numerical local Langlands correspondence, I mean, with some added things to this, that allowed them to do it in general, just by working with supercuspidal representations. This is an extremely important. This and
I mean, the Bernstein-Zelinsky classification is also required to deduce.
sorry.
You need the results of Bernstein and Zelinsky to extend the cuspidal case to the fully reducible.
Right, but Enyart did accounting for these representations by their ramification. Somehow this uniqueness is extremely important.
Yes, but the numerical correspondence. Was it to say that somehow what you get, the map that you get is subjective somehow by a counting argument?
That's right.
Yeah. Okay. By fixing some level.
I'm sorry, is the know about for n prime?
Sorry,
Is that for every n greater than equal to
n prime
greater than
1.
1?
It's 1.
Is there only a characterization like this for GLN?
Sorry.
Is there only a characterization like this for GLN?
For other groups, there are different characterizations these days using what are called endoscopic identities. But characterizations of this form, there's definitely one for generic representations of SO2n plus 1, for example. This is a rigidity theorem of Jipoa-Jiang and David Sodry. And so, yeah, such characterizations are possibly expected for generic representations. And so, those local factors for other groups, they only see the L packet of the representation. So the best you can hope for is the characterization of the L packet. And tempered L packets are supposed to contain, if you fix a non-degenerate character psi, a unique generic representation. So you could expect the characterization of generic representations, such factors. But yes, nothing this form.
This workshop, the idea was to make it a little bit different from all this workshop that only ended with GL2, but we don't want to go general either. So like GLN was a good compromise. Like a little bit more general, but not.
Can I ask a follow-up question to that? Because I actually don't know the answer to this. So you don't get something as nice for the local Langlands correspondence that the availability representation determines the representation itself, just the L packet. But do you still get the uniqueness of such correspondence? If you can come up with any other local language correspondence, for instance, for GSP4, it is still the case that as long as it satisfies some compatibilities. That
Yeah, so I don't know for what group it is proved, definitely for SO2n+1, but definitely it is accepted, expected, yeah, that if you for classic, at least for classical groups, because for classical groups, in general, the Rankin setback factors, which are obtained via the doubling method, for example, if you consider you twist representations of a classical group by representations of GLN. And so these kind of factors are expected to characterize the packets, the generic representations.
Yeah, for classical groups, that thinking, some of it's intertwined with this thinking. It was, let's just say GSP4, just for concreteness. Then there is a transfer to GL. That's the language is almost tautological. Four-dimensional representation. We make some identification of GSP4. And so the GSP4 cross GL3 or GL2 is almost like GL4 cross GL3, GL2. And I mean, even in this Arthur's, so Arthur's classification of classification for classical groups, there is a global and a local, and the local story has local language correspondence, but parameters are coming from the GLN.
Yeah, for classical groups, you can somehow parameterize a representation of classical groups via representations of GLN with some extra symmetries. This is the transform map.
Oh, yes, so it's great for lunch, and since everything was delayed by half an hour, to 2:30.
And we have switched with Joe's. Joe's.
Yeah, I'm gonna go first. Thank you again.
Thank you. Do you remember I was using the Whittaker models, the Rankin setback method? Sorry, yeah, that's very good comment. I defined it for a generic representation, but there's an extension of using the same method for only reducible representation using the non-one station theorem. You see the standard workbook that I defined? It has a Whittaker model.
Okay.
And so by definition, yeah, I do the same trick for the Whittaker model of the standard module lying above my reducible representation. And I define this to be defined from L function, which is the L function of the pair of two.
Yeah, I don't know where.
Yeah,
Yeah,
that's
exactly
fine,
where I
yeah.
thought we were at today. Okay, we're gonna go back on the market.
Function for the driver.
So same place yesterday.
We can.
Oh, no. Picture, move the front.
Oh.
Kind of extend that. That's standard representation is generic. That's what we take over. Previously, we defined L function for L prefix. L function for high-end source.
Then you got this returns that come from yeah, like it's This is that actually coming from the original. Sure, but that's a little bit different because of them different processes. You're paying transfer it with some